Hello everyone, good morning. This is Mr. Dakshinamurthy, Assistant Professor, Department of Artificial Intelligence and Machine Learning. I am handling subject 22 CS 302, Computer Organization and Architecture for the class second year and fourth semester. Today's topic is pipelining hazards. Already we know there are 5 different operations is carried out for execution of particular one instruction. These are instruction fetch, instruction decode, execute, memory and write back. Similarly, we can see in this example there are 5 instructions: add R1, R2, R3, in which R2 and R3 are the inputs. With these inputs, we are doing addition operation. After performing the addition operation, the result will be stored in R1 register. That is why the resultant register is underlined and differently colored. And this output of addition operation is the input for subtraction instruction, AND instruction, OR instruction and XOR instruction. Here the first instruction can able to provide output at the clock cycles 5 only, but these inputs can be given after 5th cycle only, but we are the subtraction instruction and instruction OR and XOR instruction having data dependency with the first instruction. So it is represented red lines. So that means data dependency in the earlier clock cycles will create the problem. That means hazard, data hazard. So in that case, subtraction and AND, OR and XOR operations can be executed with some of the junk input. That means randomly generated input. So we will get ultimately we will get some other wrong answers. The resultant registers R4, R6 and R8 will contain wrong answers after performing the addition and OR. To resolve this issue, we have to take some more steps. That means either we have to delay the operations of subtraction and OR. These 3 instructions should be delayed to the required level. Say suppose we are getting answer at a clock cycle 5. Until then, this second, third and fourth instructions could be delayed, and then it is performed after CC5, so that data dependency hazard can be eliminated. And another way, we are having a forwarding technique. These 2 techniques we will discuss in the forthcoming slides. Here, last instruction, XOR instruction, won't be affected because this instruction require a data of first instruction output after CC5. So it is that line itself indicated in the green line. So XOR instruction will get the completely executed without any problem. Whereas R instruction also we can get a proper output, that means fourth instruction we are discussing. Or here we are having dependency with the first instruction, but the CC5s can be the time cycle, the clock cycle, entire clock cycle, in which first half of the clock cycle we can complete the operation of addition, and we can pass that information, data, output resultant information, pass to the fourth instruction, the second half of the clock cycle 5. So that will be clearly shaded here. The first half of the clock cycle addition is completed, so that resultant value is passed to the fourth instruction in the second half of the CC5. So two instructions will get executed without any problem, whereas subtraction and AND instruction alone will produce something randomly generated output. For that, what we are doing is, we are introducing the minimizing stalls via data forwarding. When we are stalls or delay or bubble is introduced, remaining two instructions whichever affected, like subtraction and AND, here we are doing data forwarding. For that, we are introducing the buffer unit, temporary storage unit between all these 5 units, like between instruction fetch and instruction decode, one buffer is introduced, and instruction decode and instruction execution, another buffer, like instruction execution and data memory, another buffer, and data memory and between the write back register. There are 4 buffers we are using, so that we can forward the resultant value with the hardware wire buses, so that we can get the output of first instructions output wherever we want. We can directly forward it through using forwarding hardwire cables. Data assert classification, it has 3 different classification data asserts are there: read after write, write after write, write after read. So we'll see one by one. Read after write. Use data forwarding to overcome this problem. Even then, after changing the data memory value, we are reading it. So this can be eliminated. Use data forwarding to overcome this. Write after write arises only when writes can happen in different pipeline stages. That we can see in this diagram. Load R1, 0 R2. So content of R2 register is loaded into R1 register, and then adding R2 and R1 register, result will be stored in R1. Already we wrote the value of R2 into R1. Now R control asserts, here we can see that branching taken and not taken operations, fetching, decoding, execution and write back, and there are 11 cycles how this operation is carried. See, by seeing this 8th cycle itself, here execution is completed for the 7th instruction. Here there are 7 different instructions are fetched in the in section 5. So in section 1, in section 2, then due to branching we are directly going to the in section 7, but it takes some time for comparing and branch branch prediction. So 3 and 4th cycle we required some timing branch taken, due to that we are jumping to the in section 7. Instead in section 3, 4, 5 and 6, 4 instructions are skipped. Then similarly in section decode, here the second cycle of the instruction, here first instruction is decoded, and then 3rd cycle we are performing the second cycle decode, and 6th cycle we are performing the 7th instruction decode. Similarly execution also is carried successive manner, but the delay is carried in each and every operations, 2 cycles of delay. Because of that, 1 into 3 and then 5 into 1, there are 8 cycles, or in the alternative way 6 into 1, 6 into 1 and 1 into 2, 8 cycles. So we will discuss in detail here the same concept. Let us assume the program contains 100 instructions in which 20 are branch taken and 80 are non-branching instructions. Non-branching instructions generally without any comparison and branch taken comparison operations, it takes 80 into 1 only, 1 cycle, whereas branching instructions it required 2 cycles of comparison and branch taken delay. Normally it takes 1 cycle, due to branching operation 3 cycles it is taking. So 20 branch instruction means it takes around 20 into 3 plus 80 non-branching instruction, 80 into 1, then we are getting 140. Because of this CPI is increased 1 to 1.4, we are getting some kinds of performance lag that can be improved by rearranging instructions, or we can resolve by doing control hazard dynamic branch prediction technique, such a 2-bit branch prediction. We can eliminate these kinds of control hazards. Thank you.